Take a deep, slow breath in and let your body settle into the comforting support beneath you. Release the tension of the day as we turn our attention to the gentle, unseen world awakening just outside your window. There is something deeply comforting about the very early days of spring, that quiet transition period when the world still looks asleep but is secretly thrumming with invisible activity. Right now, if you were to sit beside a cool glass window and look out at the bare branches of the trees, you might think nothing has changed since the depths of winter. But a monumental shift is already underway, dictated by the flawless mathematics of our solar system. As we approach the vernal equinox, the sun crosses the celestial equator. Because of this astronomical alignment, the sun's angle in the sky is currently increasing by exactly 0.3 degrees every single day. That might sound like a minuscule fraction, but it changes everything. As that angle climbs, the sunlight traveling through the glass of your window feels just a little bit warmer. Out in the natural world, the plants are waiting for exactly this kind of light. They do not just feel the warmth, they actually measure the daylight. Through a biological process called photoperiodism, trees and plants detect the gradually lengthening days using a specialized photoreceptor protein called phytochrome. When the sunlight touches the branches, this microscopic protein physically changes its molecular shape, acting like a tiny silent alarm clock inside the plant's cells, signaling that the long dark is over. Even as you watch the lingering patches of winter frost slowly recede, the surface of the Earth is undergoing a profound thermodynamic transformation. You see this every year. But did you know it comes down to a property called the albedo effect? When the ground is covered in white snow, it reflects about 80% of incoming solar radiation back into space. The Earth stays cold. But the moment the dark, bare soil begins to peek through, that reflectivity drops dramatically to between 10 and 20%. The exposed dark Earth suddenly begins absorbing massive amounts of solar heat, accelerating the thaw in a beautiful cascading rhythm. As the sun bakes the damp ground, a deeply familiar scent often rises into the air, drifting through an open window to greet you. It is that rich, junky, earthy fragrance we instantly associate with early spring. This comforting aroma is caused by a chemical compound called geosmin, which is produced by a specific type of soil-dwelling bacteria known as streptomyces. As the soil thaws and the bacteria activate, they release this scent into the damp air, and your body is remarkably attuned to it. Evolutionary biology has gifted the human nose with such an intense sensitivity to geosmin that we can detect it at a concentration of just 5 parts per trillion. To put that into perspective, that is the equivalent of sensing a single drop of liquid in an Olympic-sized swimming pool. It is a biological memory built into your very DNA, a sensory reminder that the frozen Earth is breathing once again. Beneath that aromatic thawing soil, another invisible metric is being reached. Tree root systems, which have been entirely dormant, only begin to wake up when the soil temperatures reach a specific threshold, hovering right around 40 to 45 degrees Fahrenheit, or 4 to 7 degrees Celsius. Once the soil absorbs enough solar radiation to hit that temperature, the roots begin taking up water. If you were to step outside and press your ear against the rough, textured bark of a maple or a birch tree right now, you wouldn't hear it. But inside the trunk, there is a rushing river defying gravity. The mechanics of early spring sap flow are a marvel of natural engineering. It relies entirely on the delicate temperature dance of these transitional weeks. During the day, when temperatures rise above 40 degrees Fahrenheit, the tree's internal gases expand, creating positive pressure in the microscopic tissue called the xylem. Then, when the sun sets and temperatures drop back below freezing, the tree contracts, creating negative pressure. This daily freeze and thaw cycle operates like a massive natural pump. It creates an internal pressure of up to 40 pounds per square inch within the tree, a pressure greater than the air in your car tires, forcing the sugary sap upward from the roots to the highest branches. This water and nutrient mixture travels upward through capillary action, drawn up through microscopic straw-like tubes that are incredibly narrow, often measuring less than 50 micrometers wide. It is a slow, steady pulse of life, pushing upward to nourish the very thing we are waiting to see: the first buds. When you look closely at the tip of a branch in early spring, the buds look like tiny, tightly closed fists. They have actually been there since late last summer, waiting patiently through the snow and the ice. To survive the bitter freezing temperatures, these winter buds are wrapped in tough, overlapping protective scales called perulae. If you were to gently rub one of these scales between your thumb and forefinger, you would notice it feels slightly sticky or waxy. This is because the plant coats the perulae in a complex natural polymer called cutin. This waxy seal is incredibly effective, designed specifically to prevent the fragile embryonic leaves inside from losing water to the dry winter wind. But these buds aren't just hiding from the cold. They actually require it. Through a fascinating process known as vernalization, many native trees and flowering plants mathematically track the cold. In order to break dormancy and bloom, their buds must experience a prolonged period of chilling, usually between 32 and 50 degrees Fahrenheit, for a duration of 1 to 3 months. Only after this cold requirement is satisfied will the buds respond to the warming sun. It is nature's fail-safe, ensuring the delicate leaves don't emerge during a random warm day in January, only to be destroyed by the returning frost. Botanists and meteorologists track this slow progression of spring using a measurement called growing degree days. Instead of just looking at the calendar, they calculate the accumulation of heat units above a base temperature, usually 50 degrees Fahrenheit. Every day that the average temperature creeps above that baseline, a new heat unit is added to the environmental bank. As these invisible degrees accumulate, the landscape edges closer to that magical moment of bud break. In recent decades, scientists studying this phenology, the timing of seasonal biological events, have noted a phenomenon called spring creep. Because of shifting global climate patterns, the arrival of phenological spring is now advancing by about 2.5 days every single decade. When the protective scales finally peel back and the first tender leaves emerge, you might notice that they aren't bright green. Instead, the first buds of early spring often unfold in deep shades of crimson, burgundy, and pale red. This visual spectacle is due to the presence of pigments called anthocyanins. In the cool early days of the season, these red pigments act like a botanical sunscreen. They protect the vulnerable young tissues from harsh ultraviolet light, while the plant builds up its strength. It takes time for the vibrant green color to take over, because the synthesis of chlorophyll, the green pigment necessary for photosynthesis, is highly temperature dependent. Chlorophyll cannot be synthesized efficiently until the ambient air temperature consistently stays above 50 degrees Fahrenheit or 10 degrees Celsius. Until then, the world remains painted in soft, muted tones of red, silver, and pale yellow. Down at ground level, the first brave flowers are already pushing through the cold soil. Crocuses and early tulips are masters of this volatile weather. If you watch a crocus on a cool spring morning, its petals are closed tight, wrapped like a protective cocoon around its delicate center. But as the afternoon sun warms the air, the flower seemingly blooms before your eyes. This movement is a physiological response called thermonasty. It isn't actually the flower opening and closing like a door. It is rapid, localized growth. When the temperature reaches about 60 degrees Fahrenheit, the cells on the inside of the crocus petals suddenly begin growing 10% faster than the cells on the outside, forcing the flower to curve outward and open. When the cool evening air returns, dropping down to 45 degrees, the outer cells grow faster, pushing the petals back into a closed, protective teardrop shape for the night. Even the snow itself harbors microscopic signs of life during this thaw. On a mild day, you might see what looks like a dusting of fine black pepper scattered across a melting snowbank. These are springtails, often called snow fleas, though they aren't fleas at all. These tiny harmless arthropods possess an incredible biological adaptation. Their bodies synthesize a specialized glycine-rich, anti-freeze protein that binds to ice crystals inside their cells, preventing them from freezing solid. They emerge to feed on microscopic fungi, a true testament to life's resilience in the margins of winter. All of these quiet cellular miracles happen against a backdrop of shifting atmospheric physics. Spring is often accompanied by a restless howling wind, rattling the window panes as you sit comfortably inside. There is a meteorological reason for this blustery weather. During early spring, the Earth's equator warms up rapidly under the direct sun, but the polar regions remain locked in freezing darkness. And this massive temperature contrast creates deep, powerful pressure gradients in the atmosphere. The atmosphere constantly attempts to balance these extremes, resulting in the characteristic rushing winds of March and April. As these weather systems move, spring storms frequently feature rapid drops in barometric pressure. The pressure can fall by as much as 1 millibar per hour. This falling pressure acts like a massive vacuum, drawing rich, moist air up from the southern latitudes, pulling heavy rain clouds across the sky. Yet, despite this influx of weather, the northern hemisphere actually receives about 3.5% less total solar radiation during its spring than the southern hemisphere does during its corresponding season, all due to the slightly elliptical shape of Earth's orbit around the sun. And there is an intricate mathematical poetry to all of this. The changing angles of sunlight, the pressurized sap, the molecular locks and keys inside the plants. It is all happening right now, just outside your window, a massive, orchestrated awakening. That quiet orchestration unfolding outside your window is part of a legacy that humans have been trying to decode for centuries. Long before we had satellites measuring the atmosphere or microscopes examining cellular proteins, early observers recognized the profound mathematical precision of this seasonal shift. We have always sought comfort in the predictability of the returning sun. Consider the court officials in Kyoto, Japan, during the reign of Emperor Saga in the year 812 AD. As they sat in the imperial pavilions, observing the shifting weather, they began meticulously recording the exact dates when the local cherry trees broke their winter dormancy and reached full bloom. They were simply tracking a beautiful annual festival, but unknowingly, they created a continuous 1,200-year-old climate data set. It stands today as the longest unbroken phenological record in human history. Through these ancient handwritten observations, modern climatologists can see the precise historical rhythm of spring, proving just how deeply tied the buds are to the microscopic variations in annual temperatures. A similar dedication took root in Norfolk, England, in the year 1736. A naturalist named Robert Marsham began a lifelong project he called the Indications of Spring. He systematically recorded 27 distinct biological events on his estate, from the first swelling of the birch buds to the unfolding of the first oak leaf. Marsham maintained these records for over 60 years. When modern scientists analyzed his family's multi-generational data, they discovered a stunning mathematical correlation. For every 1 degree Celsius increase in average February temperature, the oak leaves unfurl precisely 5 days earlier. What is happening now, out in the damp, thawing soil, is a massive exchange of energy that explains why early spring often feels so stubbornly chilly, despite the brighter sunshine. The frozen ground acts like an immense thermal sponge, and it relies on a principle called the latent heat of fusion. It takes an extraordinary amount of physical energy to change water from a solid state of ice into a liquid state. In fact, it requires exactly 334 joules of energy to melt just 1 single gram of ice. Compare that to the mere 4.18 joules required to raise the temperature of liquid water by 1 degree. This physics phenomenon creates a condition hydrologists refer to as the zero curtain effect. For weeks, the soil temperature stalls at exactly 32 degrees Fahrenheit, or 0 degrees Celsius, absorbing vast quantities of solar radiation without actually warming up. The Earth is holding its breath, doing the heavy lifting of melting the frost before it can finally allow the soil to warm and the roots to fully awaken. Picture this progression moving across the globe, not as a date on a calendar, but as a physical traveling wave. Today, Japan's meteorological agency actively tracks the Sakura Zensen, or the cherry blossom front. This invisible line of biological awakening travels northeast across the archipelago, moving at a steady average speed of 15 miles per day. It is a slow-motion tidal wave of emerging life, dictated entirely by the creeping warmth of the Earth's surface. Across the Mediterranean, the historical markers of spring arrive on the wind. The transition is often jump-started by the sirocco, a powerful wind system that carries warm air north from the Sahara Desert. These winds can reach speeds of up to 60 miles per hour as they cross the sea. Historically, ancient sailors feared the sudden shifts in weather, but this wind performs a vital ecological service. The sirocco carries up to 3 million tons of mineral-rich Saharan dust across the Mediterranean each spring. As it settles, it deposits critical phosphorus directly into the European soil, acting as a massive airborne nutrient delivery system that nourishes the emerging spring flora across an entire continent. Notice how the sound of the rain changes during these early spring weeks. As you sit comfortably inside, you might hear a heavier, more resonant drumming against the glass. Spring raindrops are often physically larger than winter rain. A typical spring raindrop can measure up to 6 millimeters across. It is held together purely by the incredible surface tension of the water molecules, forming a shape similar to a tiny hamburger bun rather than a teardrop. As these large, heavy drops fall through the warming air, they reach a terminal velocity of roughly 20 miles per hour before striking the Earth. With this heavy spring rain, sometimes comes a distant rolling rumble of thunder. The atmosphere, warming at the surface while remaining freezing aloft, begins generating an intense electrical potential difference. A single spring lightning strike can carry up to 100 million volts. While ancient farmers did not understand the atmospheric chemistry, they observed its effects. In the 1st century, the Roman author Pliny the Elder wrote in his encyclopedias that crops always grew noticeably greener and more robust following a thunderstorm. Modern atmospheric science reveals the brilliant truth behind Pliny's ancient observation. The extreme heat of a lightning bolt reaches roughly 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. This intense, localized flash of heat is powerful enough to break apart the incredibly stable triple bonds of nitrogen gas naturally floating in the atmosphere. This process, known as atmospheric nitrogen fixation, bonds the newly freed nitrogen with oxygen to create water-soluble nitrates. The heavy spring rain then washes these nitrates out of the sky, delivering approximately 10 million tons of natural high-quality fertilizer to the Earth's surface globally every single year. The rain you hear against the window is literally bringing down the raw building blocks of life, preparing the soil for the buds to burst. As the storms pass and clear skies return, the resulting spring mornings often create fascinating, localized microclimates. Through a process called radiant cooling, the heat gained during the day escapes rapidly back into a cloudless night sky. Because cold air is denser and heavier than warm air, it drains down the hillsides like invisible molasses, pooling in the lowest elevations. This creates temperature inversions known as frost hollows. The bottom of a quiet valley can record temperatures up to 15 degrees Fahrenheit, colder than the slopes just 100 feet above. This is why you will historically see ancient orchards and vineyards planted halfway up a hillside rather than in the fertile valley floor. Early agriculturists knew the cold air would sink, and planting on a slope protected their delicate first buds from the lingering spring frost. Over the lakes and ponds, this early season temperature inversion, where slightly warmed spring air sits heavily over freezing, icy water, bends the very light waves traveling through the atmosphere. It creates an optical phenomenon known to meteorologists as a superior mirage. The cold air traps the light and bends it downward in a ducting effect, making distant shorelines or islands appear to magically float above the horizon. Deep within those lakes, a mechanical marvel of spring is silently occurring. As the surface ice slowly melts away, the cold water beneath undergoes a unique physical transformation. Water is the only known non-metallic substance on Earth that expands when it freezes, which is why ice floats. But as the spring sun warms that icy meltwater, it reaches its absolute maximum density at exactly 39.2 degrees Fahrenheit, or 4 degrees Celsius. Because this specific temperature makes the water heavier than both the ice above it and the warmer water below it, this dense layer suddenly sinks straight to the bottom of the lake. This massive invisible plunge pushes the nutrient-rich bottom water up to the surface. Limnologists call this the spring turnover. This physical mixing cycle distributes dissolved oxygen to the deep water organisms and brings a wealth of dormant minerals into the sunlight. This immediate influx of nutrients triggers an explosive, microscopic bloom of phytoplankton, effectively waking up the entire aquatic ecosystem in a matter of days. From the shifting of Saharan winds to the electrical chemistry of a thunderstorm, every element of this season is deeply interconnected. The very fabric of the landscape is currently undergoing millions of calculated changes, a grand thermodynamic cycle that humanity has watched, documented, and marveled at for millennia. And all you need to do is sit peacefully, listen to the rain, and observe the invisible machinery of the waking world. That invisible machinery of the waking world, so carefully tracked by ancient scholars and modern scientists alike, relies on physical mechanisms that are surprisingly familiar to us. If you sit quietly and observe the natural world through the glass, the complex science of the changing season often perfectly mirrors the simple, everyday objects inside your own home. Look closely at the swelling branch tips of a nearby tree. Inside those tightly bound capsules, the biological engineering rivals human aerospace design. The complex geometry of how an embryonic leaf is folded inside a bud is scientifically known as vernation. The mechanics at play here heavily resemble the meticulous packing of a skydiver's parachute or the precise overlapping creases of intricate origami. Nature has a space problem in early spring. It must protect large, fragile solar panels inside an impossibly small, weatherproof casing. To solve this, species like the beech and the hornbeam utilize plicat vernation. This means their embryonic leaves are sharply pleated, folded back and forth upon themselves, exactly like a closed accordion or a paper fan. This brilliant geometric arrangement allows a single leaf, which will eventually reach a flat surface area of 10 square inches, to remain perfectly compressed inside a bud smaller than a single dried green pea. By folding the tissue rather than simply rolling it, the plant ensures the delicate cellular structure will not tear during the explosive growth phase to come, a phase where the leaf will increase its size by up to 100 times in a matter of mere days. Deep beneath the yielding wet earth, millions of dormant seeds are simultaneously waking up through a completely different mechanical process called imbibition. Think of a completely bone-dry kitchen sponge resting on a counter. If you drop it into a sink full of water, the rigid cellulose immediately draws the moisture into its empty spaces, swelling and softening almost instantly. A seed waking from winter dormancy acts just like that dry sponge. Its hard outer coat contains microscopic tunnel-like pores. As the frozen soil thaws, these pores eagerly draw in the surrounding moisture, causing the seed to swell to over 200% of its original dry weight. This rapid influx of liquid generates an incredible internal force known as turgor pressure. This invisible hydrostatic pressure builds up within the plant's cellular walls, reaching an astonishing 1,000 pounds per square inch. To put that monumental force into everyday terms, that is roughly 10 times the pressure generated inside a standard household water heater, or the equivalent of the water pressure found thousands of feet down at the bottom of the ocean. It is this sheer hydraulic strength that allows a fragile, tiny seed to easily shatter its thick outer shell and gives a delicate green shoot the power to effortlessly push its way up through dense, heavy clay, or even crack solid concrete pavement. As all that moisture moves through the earth, you might notice the distinct, squishy feeling of spring mud forming just beyond the porch. Creating a healthy environment for these new roots is remarkably similar to baking a well-aerated cake. A baker uses yeast or baking powder to create tiny air pockets, ensuring the cake isn't a solid, heavy brick. Nature requires the exact same structure. Ideal, healthy topsoil is actually composed of exactly 50% solid material, minerals, sand, and organic matter, and 50% completely empty pore space. Throughout the winter, the freezing groundwater expands inside these tiny earthen pockets, creating a geological microchurning process called cryoturbation. This seasonal freeze and thaw cycle acts exactly like yeast in bread dough. It naturally heaves and aerates the soil, actively preventing the earth from becoming permanently compacted under the weight of winter snows. When the ground finally thaws, it leaves behind a perfectly textured, sponge-like matrix beneath the grass, capable of holding an astonishing 20,000 gallons of fresh water per single acre. When you glance out the window early on a crisp spring morning, you might spot tiny droplets sparkling at the very tips of the newly emerged grass blades. While it is easy to assume this is morning dew, it is very often a different phenomenon entirely, called guttation. The mechanism behind guttation functions exactly like a pressure relief valve on a steam engine. During the night, when the damp spring soil is heavily saturated, but the cool air prevents normal evaporation from the leaves. The intense water pressure inside the roots continues to build. To prevent the plant's internal plumbing from rupturing, the grass actively forces the excess water out through specialized microscopic pores at the tips of the leaves, known as hydothodes. The sparkling beads you see are the literal exhaust of the grass, working overtime in the damp spring soil. Hovering just above that damp lawn, you will frequently witness a thick, rolling blanket of early morning spring fog. This specific type of weather is called radiation fog, and it forms using a principle similar to an overflowing glass of water. Imagine carefully pouring water into a tall glass until it crests just over the brim and begins to spill down the sides. The atmosphere functions just like that glass. At any given temperature, it can only hold a specific, finite amount of invisible water vapor. As the clear spring night cools the air down to its exact dew point, the relative humidity hits precisely 100%. The atmospheric glass is entirely full. Because the cooling air can no longer hold the moisture in a gaseous state, it spills over, condensing into liquid onto microscopic airborne particles called condensation nuclei. These resulting fog droplets are incredibly minuscule, typically measuring only 10 to 15 micrometers across, less than the width of a human hair. Because they lack any real mass, a single fog droplet falls through the air at a glacial pace of about 1 centimeter per second. If you were to release one of these microscopic water spheres from the ceiling of your room, it would take over 2 hours for it to gently drift down to the floor. As the morning sun rises and clears away that hovering fog, the damp earth begins to heat up rapidly. This sudden warmth is dictated by Lambert's cosine law, an equation of optical physics that you have likely experienced in a dark room. If you take a flashlight and shine it straight down onto a table, you create a tight, intensely bright, and focused circle of light. But if you tilt your hand and shine the flashlight at a sharp, shallow angle, that exact same amount of light stretches out into a dim, elongated, and much weaker oval. During the winter months, the low-angled sun functions like the tilted flashlight, spreading its energy weakly over a vast, elongated area of the hemisphere. But as the vernal equinox shifts our planetary tilt, the sun's elevation climbs higher. The incoming solar radiation is suddenly concentrated into a much tighter, more direct footprint. By mid-April in the temperate mid-latitudes, a single square meter of Earth receives nearly double the solar energy it absorbed back in December. This intensely focused, uneven heating across the landscape creates columns of rising warm air, called thermals. Darker surfaces like freshly plowed agricultural fields absorb solar radiation much faster than pale, dormant meadows. The air directly above these dark soils heats rapidly, detaches from the ground, and floats upward. These thermals function exactly like invisible atmospheric elevators. Returning migratory birds, such as broad-winged hawks and eagles, are masters of reading this invisible architecture. They actively seek out these rising columns, where the warm air travels upward at a rate of 10 to 20 feet per second. By spreading their wings and simply stepping into the thermal, these heavy birds ride the invisible elevator to the top. By seamlessly gliding from the top of one thermal down to the base of the next, migratory flocks can travel up to 250 miles in a single day without having to flap their wings even once, perfectly conserving their metabolic energy for the long journey north. Even in the most shaded corners of the yard, where patches of winter snow stubbornly cling to the shadows, small biological changes are interacting with the sun. Sometimes, late spring snow takes on a faint, slightly pinkish hue. This is caused by a microscopic cold-loving organism called Chlamydomonas nivalis, a type of specialized algae. The mechanics of this algae speed up the arrival of spring using a principle you feel every summer. Think of how wearing a heavy black shirt on a sunny July afternoon makes you feel significantly hotter than wearing a crisp white one. Dark colors absorb light, while light colors reflect it. To protect themselves from the increasingly intense ultraviolet rays of the spring sun, these microscopic algae produce secondary red carotenoid pigments, acting as a biological sunscreen. This red tint slightly darkens the surface of the snowbank, lowering its albedo, or its reflective capacity, by up to 13%. By donning this microscopic dark shirt, the snowbank absorbs significantly more of the sun's radiant heat, forcing the stubborn ice to melt faster and making way for the first true buds of the new season. Everywhere you look, the landscape is utilizing pressure, geometry, and focused energy to shake off the cold, transforming the quiet view outside your window into a masterpiece of everyday physics. What is happening now, out in the damp, thawing soil and the increasingly bright sky, is not just an isolated environmental event. It is a massive, interconnected shift that directly involves you. We often look at the budding trees as if they are entirely separate from our own lives, a pretty background to our daily routines. But the very same changing sunlight that awakens the dormant oak tree is actively reprogramming your own biology right now. Consider the light inside your home as you look out the window. A typical indoor living room is illuminated at roughly 300 to 500 lux, a standard measurement of illuminance. That might feel perfectly bright to your eyes, but it is a mere shadow compared to the raw power of the emerging season. Even on a slightly overcast spring morning, the natural light outside hits between 10,000 and 25,000 lux. In direct spring sunshine, it spikes to an astounding 100,000 lux. When you sit by the glass and let that bright spring light wash over your face, microscopic receptors in your eyes called intrinsically photosensitive retinal ganglion cells, or iPRGCs, capture those photons. These specialized cells don't help you see shapes or colors. Their sole purpose is to measure the length and intensity of the daylight. They instantly send an electrical signal deep into the center of your brain, hitting a tiny cluster of neurons known as the suprachiasmatic nucleus. Just as the phytochrome in the tree branches acts as a botanical alarm clock, this neural cluster is your biological metronome. The intense spring light actively suppresses your production of melatonin, the sleep hormone, while simultaneously flooding your system with serotonin. You are, quite literally, photoperiodic, waking up from the winter shadows in the exact same biological rhythm as the first green shoots in the garden. Deep within your own skin, another chemical reaction is currently mimicking the life cycle of the foliage. As the vernal equinox shifts our planetary tilt, the atmosphere overhead physically changes the way it filters solar radiation. During the winter months, the steep angle of the sun means its rays must pass through a much thicker slice of the ozone layer, which aggressively scatters and blocks ultraviolet B radiation. But right now, as the sun climbs higher in the sky, that pathway shortens. More ultraviolet B begins to successfully penetrate the atmosphere and reach the surface. When this specific wavelength of light touches your skin, it interacts with a compound in your epidermis called 7-dehydrocholesterol. The sheer kinetic energy of the solar radiation actually breaks a specific carbon bond within this molecule, instantly converting it into previtamin D3. As you sit comfortably by the window, enjoying the warmth, you are essentially performing a human version of photosynthesis, absorbing the sun's energy to manufacture your own vital structural nutrients. You and the budding leaves are utilizing the exact same celestial energy source to build your strength for the coming year. Notice how the air changes right before a fresh spring shower rolls across the neighborhood. You might slide the window open just an inch to let the breeze inside, and suddenly you catch a very sharp, distinct, and uniquely clean scent. We previously explored the earthy smell of geosmin rising from the wet soil, but this pre-rain fragrance is completely different. It is an atmospheric gas called ozone, mathematically represented as O3. Up in the turbulent clouds of a spring storm, powerful electrical charges are constantly moving. Even before a lightning bolt visibly strikes the ground, the intense electrical fields inside the cloud split the stable two-atom oxygen molecules, O2, that naturally make up the air. These newly freed singular oxygen atoms immediately seek out other pairs, combining to form the three-atom structure of ozone. This newly minted gas has a pungent, almost metallic odor, somewhat similar to chlorine. The powerful rushing downdrafts of the approaching spring storm act like a massive atmospheric broom. They sweep this ozone gas from elevations of 10,000 feet, pushing it rapidly down to ground level, just ahead of the rain. The human olfactory system is astoundingly tuned to this specific molecular shape. You can detect the crisp smell of ozone at a concentration of just 10 parts per billion. Your body recognizes this scent as a primal cue, a sensory promise that the atmosphere is about to deliver heavy, life-giving water to the thirsty spring buds. At this very moment, as those buds begin to fully peel open and expose their tender leaves, they are preparing to participate in a planetary respiration cycle that alters the chemistry of the entire globe. Once the leaves unfurl, they open microscopic pores on their undersides, called stomata. Through these tiny openings, the trees begin eagerly pulling carbon dioxide out of the air to fuel their rapid growth. Scientists discovered the sheer magnitude of this process by establishing the Mauna Loa Observatory in Hawaii, where they track the global concentration of atmospheric carbon. Their continuous data creates a famous jagged graph known as the Keeling curve. If you look at this graph, you will see an incredible repeating pattern. Every single year, starting in early May, as the Northern Hemisphere's vast temperate forests fully leaf out, the total global level of carbon dioxide drops dramatically by about 6 to 7 parts per million. Roughly 25% of all the carbon dioxide in the entire atmosphere is actively drawn down and temporarily locked into the growing foliage. Think of the Northern Hemisphere not just as a collection of individual trees, but as a single, massive, biological lung. Right now, in early spring, the Earth is taking a long, deep, restorative inhalation. To accomplish this colossal growth, the trees must first secure their future, leading to a phenomenon you might find resting quietly on your windowsill. In mid to late spring, a fine pale yellow dust often settles over the glass, the porch, and the surrounding cars. While it might look like mere dirt, it is actually a marvel of aerodynamic engineering. Many early blooming trees, such as oaks and pines, rely entirely on wind pollination, a process scientifically termed anemophily. Because they don't produce showy nectar to attract bees, they must trust the spring breezes to carry their genetic material. Picture this incredibly precise evolutionary strategy. A single mature oak tree can produce up to 1 billion individual grains of pollen in a single spring season. But the pine tree takes the engineering even further. If you were to look at a grain of pine pollen under a powerful scanning electron microscope, you would see it isn't just a round sphere. It features two tiny hollow appendages extending from its sides, called saxi. These are literal microscopic air bladders, functioning exactly like two tiny hot air balloons attached to the sides of the pollen grain. These bladders make the pollen so incredibly buoyant that a steady spring wind can carry it at altitudes of 2,000 feet, drifting for distances of up to 500 miles before finally returning to the ground. That pale yellow dust on your window has potentially traveled across entire mountain ranges just to land there. There is an even larger force dictating this seasonal transition, one that operates far beyond the clouds and the drifting pollen. The long-term rhythm of spring is deeply tied to the interaction between our planet and the magnetic weather of deep space. Spring brings a statistical peak in geomagnetic activity, meaning the months of March and April feature the highest frequency of the aurora borealis, or the northern lights. For decades, this equinox aurora connection was a mystery, until physicists identified a mechanism called the Russell-McFerrin effect. Our planet functions as a giant magnet, possessing a massive magnetic dipole that shields us from the constant stream of charged particles flowing out from the sun, known as the solar wind. For most of the year, the Earth's magnetic field is angled in a way that successfully deflects this incoming energy. But as the Earth reaches the vernal equinox, its planetary tilt perfectly aligns our local magnetic field geometry with the Sun's interplanetary magnetic field. This perfect temporary alignment acts like a cracked door in a fortress. It causes the magnetic fields to briefly link together, creating openings called reconnections. Through these invisible doorways, energized solar particles rush down into the Earth's upper atmosphere, colliding with oxygen and nitrogen at speeds of 40 million miles per hour. These collisions release spectacular bursts of glowing green and pink light, illuminating the polar skies in celebration of the returning spring. Every single detail, from the production of vitamins in your skin to the microscopic air bladders on a grain of pollen, up to the magnetic connection between the Earth and the Sun, is fundamentally linked. You are not just watching the weather happen outside your window. Your biology is actively participating in the grand, turning mechanics of the season. As the magnetic architecture of the solar system ebbs and flows far above us, a much more immediate, deeply sensory shift is unfolding right at your window pane. You listen closely to the way a distant bird call or the faint hum of a faraway train reaches your ears during these early weeks. This striking auditory clarity is not an illusion. It is dictated by the precise thermodynamics of the spring atmosphere. Sound travels through the air as a longitudinal wave, and its speed is highly dependent on ambient heat, increasing by exactly 0.6 meters per second for every single degree Celsius the air warms. During the volatile transition of spring, the landscape frequently experiences temperature inversions. The thawing ground cools rapidly overnight, leaving a dense layer of freezing air trapped directly beneath a thick blanket of much warmer air aloft. Because sound waves travel faster in warm air, the upper edge of the acoustic wave outpaces the lower edge. This physical discrepancy actively bends, or refracts, the sound waves back downward toward the Earth, rather than allowing them to dissipate up into the sky. The landscape essentially functions as a massive, invisible acoustic dome, channeling distant noises across the dormant fields with brilliant, high-fidelity precision. Reach out in your mind and imagine brushing your fingers against one of the newly exposed leaf buds resting on the branches outside. Instead of the tough, leathery surface you might expect from a tree, many first buds, like those of the magnolia or the wild apple, feel incredibly soft. They are covered in a dense, velvety silver-white fuzz. These microscopic hairs are scientifically classified as trichomes. They serve a vital engineering purpose, functioning precisely like a high-tech windbreaker, layered carefully over a thermal sweater. By forming a tangled microscopic forest over the leaf's sensitive epidermis, these trichomes physically trap a stationary layer of air directly against the plant's surface. This boundary layer completely halts the kinetic energy of the spring wind, preventing the breeze from stripping away the plant's vital moisture through evaporation. During a frosty, unpredictable spring night, this trapped cushion of stagnant air remains up to 5 degrees Fahrenheit warmer than the surrounding breeze. This tiny, isolated microclimate successfully keeps the fragile cellular water locked inside the leaf safely above the freezing point of 32 degrees. When those fuzzy coverings finally peel away, the newly emerging leaves often display a distinct, mirror-like sheen. This initial glossy texture is the direct result of a fresh coating of epicuticular wax. When a leaf first breaks its dormancy, its protective wax barrier is composed of simple, unlinked lipid molecules. Because these lipids have not yet been degraded by harsh summer ultraviolet radiation, nor cross-linked into a hardened, textured crust, they form a perfectly smooth, flat surface on a microscopic level. As the morning sunlight strikes this pristine wax, the photons reflect almost uniformly in a single, unified direction, a physics phenomenon known in optics as specular reflection. The light bounces off the new foliage cleanly, creating that wet, glistening appearance we associate with fresh growth. It is only later in the season, as the wax chemically hardens and begins to roughen under the elements, that the light will scatter chaotically in multiple directions, permanently turning the shiny spring foliage into a matte, flat green. Look beyond those glistening leaves and gaze up into the overarching sky. You may observe that the color of the heavens has subtly shifted from the deep, piercing sapphire of January to a softer, slightly hazy, pale blue. This visual softening is a direct, measurable indicator of changing humidity levels. As the frozen earth thoroughly thaws and releases its stored winter water, the atmospheric vapor content drastically increases. These newly suspended water molecules are physically massive compared to the tiny oxygen and nitrogen molecules naturally comprising the air. When the incoming solar radiation hits these larger water droplets, it triggers an optical process called scattering. Unlike the winter atmosphere, which utilizes Rayleigh scattering to selectively bounce only the short blue wavelengths of light, scattering bounces all visible wavelengths, red, green, and blue, equally in every direction. This newly scattered white light mixes thoroughly with the blue background, washing out the harsh contrasts of winter and painting the muted pastel canopy so uniquely characteristic of early spring afternoons. Pay attention to the specific, complex scent that rises when the very first gentle rain showers strike the dry spring pavement or the dusty garden soil. While we previously explored the deep, damp smell of soil bacteria, the sharp, almost sweet fragrance that occurs at the exact moment of rainfall relies on an entirely different mechanism. The scientific term petrichor was coined by Australian researchers in 1964 to accurately describe this exact chemical reaction. During the dry, breezy days before a storm, local plants continuously exude specific botanical oils, primarily palmitic and stearic fatty acids. These oily compounds are absorbed and hoarded by porous rocks, concrete, and dry clay. When a spring raindrop finally strikes this dry, porous surface at a terminal velocity of roughly 20 miles per hour, it forcefully traps microscopic pockets of air beneath it. These trapped air pockets instantly dissolve into the water drop, but they immediately rebound, shooting upward through the liquid. The mechanics at play here behave exactly like the tiny effervescent bubbles racing to the surface of a freshly poured glass of champagne. As these microscopic bubbles violently burst at the surface of the raindrop, they launch invisible aerosolized droplets into the wind. These buoyant aerosols carry the stored fatty acids and plant oils directly up to your olfactory receptors. A light, misty spring drizzle is incredibly efficient at generating this scent profile. Conversely, a heavy torrential downpour actively suppresses the fragrance by instantly flooding the porous surfaces, completely preventing the aerosol bubbles from forming. That is precisely why the most intoxicating, fragrant spring days are always accompanied by the lightest, most delicate mists. Above this fragrant moisture, the returning thermal heat paints entirely new shapes across the horizon. The classic fluffy white clouds of spring, with their distinctly flat bottoms and cotton-like tops, are categorized by meteorologists as cumulus humilis. Their precise floating geometry is a perfect visible representation of atmospheric math in action. As the dark, freshly thawed soil absorbs the sun's radiation, it intensely heats the localized pockets of moist air directly above it. Because warm air possesses less density than cold air, these invisible columns of moisture detach from the ground and float upward. But as this air mass rises, the atmospheric pressure around it drops, allowing the air column to expand. This physical expansion forces the air to cool at a strictly defined mathematical rate called the dry adiabatic lapse rate. In the Earth's lower atmosphere, this rate equals exactly 5.4 degrees Fahrenheit of cooling for every 1,000 feet of vertical elevation gained. Eventually, the rising column of air cools to its exact dew point, the absolute temperature threshold where it can no longer support water in a gaseous state. At this exact altitude, a boundary line, known as the lifting condensation level, the invisible vapor instantly flashes into visible liquid cloud droplets. Because the temperature and humidity of the rising air mass are generally uniform across a specific region, this rapid condensation happens at the exact same elevation across the entire sky. The flat, dark base of a cumulus humilis cloud is not merely a random shape. It is a perfectly level visible ceiling in the atmosphere. In early spring, this precise boundary typically sits at an altitude of approximately 3,000 to 4,000 feet, drawing a distinct, horizontal line in the sky where the physical properties of the air abruptly and beautifully change state. Every texture you could possibly imagine, every muted color the sky presents, and every subtle aromatic shift in the damp breeze is driven by these strict, beautiful laws of thermodynamics and biology. The environment outside your window is constantly calculating, expanding, and physically adapting to the returning heat, creating a perfect symphony of sensory science. As the sun finally begins to dip below the horizon, a completely new sequence of events initiates just outside your window. The transition from a bustling spring afternoon to a quiet, dormant night unfolds through a highly methodical, step-by-step atmospheric process. Notice how the light shifting across your room changes color as the evening advances. When the sun reaches a geometric angle of exactly 0 degrees relative to the horizon, the sunlight must travel through a significantly longer slice of the Earth's atmosphere. In fact, during this precise twilight window, the atmospheric path length increases by roughly 40 times compared to high noon. As the light pushes through this massive expanse of atmospheric gas, a sequential filtering process occurs. The shorter, high-energy blue and violet wavelengths are aggressively scattered away, by oxygen and nitrogen molecules. Step by step, only the longest, slowest wavelengths of visible light, the deep reds, burnt oranges, and soft purples, possess the mechanical energy required to successfully penetrate the thick atmospheric dust and reach your eyes. And this sequential scattering is why the early spring twilight paints the walls of your room in such warm, comforting hues. What's happening now is that the plants outside are actively responding to this fading light, initiating their own nightly shutdown sequence. During the day, the newly opened leaves kept their microscopic pores, the stomata, wide open to absorb carbon dioxide. But as the ambient lux levels drop, the plant begins a step-by-step water conservation protocol. First, specialized cells bordering the pores, called guard cells, actively pump potassium ions out of their internal fluid. As these ions exit, water rapidly follows them through the process of osmosis. This sudden evacuation of water causes the guard cells to lose their internal turgor pressure. Gradually, they deflate, physically shrinking and collapsing inward to perfectly seal the microscopic pore shut. This mechanical locking process completely halts transpiration, ensuring the fragile new leaves do not lose their vital moisture to the cool night air. At this very moment, with the stomata safely sealed and the sun gone, the tree begins its most critical phase of physical growth. You might assume buds expand during the warm, sunny day, but the actual physical lengthening of the cellular tissue occurs almost entirely in the dark. Scientists discovered this step-by-step nighttime engineering feat and named it the acid growth hypothesis. The sequence begins deep inside the apical meristem, the very tip of the dormant bud. First, the plant synthesizes a specialized growth hormone called auxin. Under the cover of darkness, check in. This hormone signals the cell membranes to activate millions of microscopic proton pumps. These pumps systematically force hydrogen ions outward, directly into the rigid cellulose wall that surrounds the plant cell. Step by step, this influx of hydrogen rapidly lowers the pH of the cell wall, dropping it from a neutral state down to a highly acidic level, below 4.5. This specific threshold of acidity serves as a chemical key. The low pH instantly activates unique proteins hidden in the cellulose framework, appropriately named expansins. These proteins act like tiny molecular scissors, systematically snipping the rigid crosslinks that hold the stiff cellulose microfibrils together. With the structural walls suddenly softened and loosened, the intense hydrostatic pressure built up inside the plant cell forcefully pushes outward. In a single night, this step-by-step mechanical stretching allows a newly emerging spring leaf cell to physically expand to between 10 and 50 times its original dormant volume. While the world sleeps, the forest is silently, hydraulically stretching itself into a new season. Deep within the wet, cooling woods, animal life is undergoing its own sequential shift. The tiny spring peeper, a species of chorus frog measuring barely an inch long, has spent the winter frozen solid under the leaf litter. Its survival was guaranteed by a step-by-step biological antifreeze system. During the deep freeze, the frog's liver flooded its bloodstream with massive quantities of glucose, in preventing sharp ice crystals from forming and piercing its delicate organs. Now, as the ground temperature officially stabilizes above 37 degrees Fahrenheit, a reversal sequence begins. First, the frog's heartbeat slowly resumes a steady rhythm. Next, the kidneys actively begin filtering the protective glucose out of the bloodstream, systematically lowering the blood sugar back to a normal baseline. Finally, as the muscular tissue thaws, the frog begins to draw air into a specialized vocal sac located beneath its chin. By forcefully pushing this trapped air back and forth over its vocal cords, the tiny amphibian generates a high-frequency chirp that can reach an astonishing 90 decibels, nearly as loud as a commercial lawnmower. The step-by-step thawing of millions of these frogs creates the rhythmic, overlapping chorus that defines a damp spring night. Picture this precise mathematical cooling process happening across your entire neighborhood. As the sky darkens, the Earth's surface begins a physical process called radiational cooling. Throughout the day, the damp soil absorbed shortwave solar radiation. Now, step by step, the ground releases that stored energy back into the vacuum of space in the form of invisible, long-wave infrared radiation. As the soil radiates its heat upward, the immediate physical surface of the ground drops in temperature much faster than the air, hovering just a few feet above it. Eventually, the blades of grass in the yard cool past a critical mathematical threshold known as the dew point, often hovering around 45 degrees Fahrenheit on a mild spring night. As soon as the surface hits this exact temperature, the gaseous water vapor suspended in the lowest inch of the atmosphere undergoes a phase change. Step by step, molecule by molecule, the vapor condenses back into a liquid state, depositing a heavy, glittering layer of condensation across the yard. The Earth is systematically wrapping itself in a quiet, thermal blanket of dew. As the evening advances outside the glass, you might transition from the window to the absolute comfort of your bed. And as you do, your own biology mirrors the step-by-step cooling and resting sequence of the natural world. Human sleep is not a sudden switch. It is a meticulously coordinated, cascading process of physiological changes. First, as the natural ambient light in your room drops below 10 lux, the intrinsically photosensitive receptors in your eyes send a final calming signal to the pineal gland situated deep in your brain. This gland immediately begins the chemical conversion of stored serotonin into melatonin. As this newly synthesized melatonin gradually saturates your bloodstream, it acts as a systemic messenger, traveling to every organ to announce the arrival of night. Next, your cardiovascular system follows a predictable downward trajectory. Your parasympathetic nervous system, the biological network responsible for rest and digestion, smoothly takes control from the active sympathetic system. Step by step, your heart rate naturally decreases by 10 to 15 beats per minute. Simultaneously, your blood vessels gently dilate in a process known as vasodilation. This widening of the vessels reduces the mechanical resistance against your flowing blood, allowing your overall blood pressure to safely dip by 10 to 20% during this nocturnal phase. As your blood flows more slowly, a critical thermal shift occurs. To successfully initiate the first true stage of sleep, your core body temperature must physically drop. By routing warmer blood out toward the surface of your skin, your body systematically radiates heat away from your internal organs, effectively lowering your core temperature by 1 to 2 degrees Fahrenheit. You are cooling down in the exact same mathematical rhythm as the spring soil outside your window. Gradually, your muscular system engages in its own shutdown sequence. The skeletal muscles, which have maintained your posture all day, systematically release their stored tension. The physical tone of your muscle fibers decreases, creating a profound, heavy sensation of relaxation that anchors you firmly into the mattress. Even your respiratory rate naturally downshifts, dropping from an active daytime rate of perhaps 15 breaths per minute to a slow, rhythmic, and incredibly steady 12 breaths per minute. Finally, the electrical activity in your brain transitions through a beautifully measured frequency cascade. The rapid active beta waves that carried you through the day begin to space out, slowing down to a calm, rolling rhythm of 8 to 12 hertz, known as alpha waves. As your eyelids grow heavy and close, these alpha waves systematically give way to the even slower, highly synchronized theta waves, pulsing gently at 4 to 8 hertz. Your thalamus, the sensory gateway of the brain, actively begins to block incoming auditory and tactile signals, gently severing your conscious connection to the waking world. Everything is following its proper natural sequence. The buds are expanding in the dark, the soil is resting under the dew, and your body is perfectly executing its own timeless rhythm of restoration. Embrace the heavy, comforting weight of this process. I am safe in this quiet transition. My body knows exactly how to rest. I am in perfect harmony with the turning season. I release the day, step by step, breath by breath. I welcome the peace of the deep, still night. Good night.